in this video we're going to start to learn about heat and how we can calculate heat or thermal energy for a substance. So heat is a little bit different than temperature. It is energy, but it's the transfer of energy between two substances because they have a different temperature. Now remember that the temperature of a substance is the average kinetic energy of the molecules. So the molecules are bouncing around when whatever that substance is. And so if you bring it near another substance, so like if you put your hand on a cold piece of metal, the high energy molecules of your hand are going to be running into the lower energy molecules of the cold piece of metal, and therefore the energy is going to be transferred to it in the form of heat. So heat always moves from hot substances to cold substances, never the other way around. So the faster moving particles or molecules of the higher temperature substance are going to transfer their energy to the slower moving molecules of the lower temperature substance. So heat is always going to transfer from higher to lower. Right? So when you think about your body on a cold day, actually what is happening is that the heat is leaving your body and going into the air, and that's why you feel cold, not because the cold is coming into you. We also talked about that when we looked at chemical reactions. So if you were to feel a beaker and the beaker felt warm, the heat was leaving the beaker and going into your hand, which is why your hand started to feel warmer. That is an exothermic reaction. When we looked at the heat in an endothermic reaction, like when we put the barium hydroxide and the ammonium thiocyanate together, it felt cold because heat was being pulled from your hand into the reaction, so it was an endothermic reaction. So we measure heat in terms of our body in calories. So calories is the heat energy that we get from our food. And 1 calorie is 4.186 joules. Joules is the unit that we use for energy in chemistry and in physics. So calories that you look at on like a food label are actually kilocalories. So they're not just calories. So when it says something's 500 calories, it's actually 500,000 heat calories. Alright, so thermal energy is a little bit different than temperature and kinetic energy. Thermal energy is the sum total of all the energy in the particles. Remember that temperature was an average of the kinetic energies of the particles, whereas thermal energy is a sum total. So heat energy or thermal energy we represent with the letter Q, and we can use it in the law of conservation of energy. Now this is just like the law of conservation of matter, where heat is neither created nor destroyed, it can only go from one place to another, or energy is neither created nor destroyed, it can only go from one form to another. So the amount of heat energy that it takes to change the temperature of a substance can be calculated with this equation, where Q is the heat energy in joules, M is the mass of the substance in G, because it takes more energy to heat a larger substance than a smaller amount of substance. C is the specific heat of a substance. Now, specific heat is a physical property. Essentially what that means is how easily will something change its temperature. We know that metals can heat up really quick and cool down really fast, whereas water, it takes a lot more energy to heat it up or a lot more time to let it cool down. And then T is the change in the temperature. So the heat energy needed to change some mass that can change its heat by some amount, by some degree or change in temperature. And we'll do some examples with this. Right? So every different substance has a specific heat, and it can have a different specific heat when it's in a different state of matter. So if we look here, you can see the specific heat, or C, sometimes it's C sub P, for different substances. So the specific heat, or the heat capacity, is the amount of heat it takes to raise 1 gram of a substance by 1 degree Celsius. So if we look at water here, liquid water is 4.18, which, remember, that's what a calorie is. So what defines a calorie is how much energy it takes to raise 1 gram of water by 1 degree Celsius. But you can see at a solid and a gas, they have a different specific heat, and then different substances here have a different specific heat. And keep in mind that on your reference table, on the front of your reference table, there's a list of specific heats for common metals. So if we look comparatively, remember one of water's special properties is that it had a high specific heat. It takes a lot of energy in order to change its temperature, and that's what stabilizes the climate on our planet. So you can see the difference between water being 4 and then looking at lead being 0.1. So there is quite a big difference. All right, so let's do an example. So remember, Q equals MC change in T. So if you have a 10-gram sample of aluminum, how much heat energy is required to raise the temperature from 15 to 25 degrees? So we have our mass, which is 10 grams. A specific heat, that's a known value, so I just have to look it up. So if I click back to this table, I can see aluminum's 0.897. And then my change in temperature would be 10 degrees, going from 15 to 25. So I got 10 grams times the specific heat of aluminum times 10, and I get that 89.7 joules is how much energy is required to heat that amount of aluminum. All right, so when a substance undergoes a phase change, so when it's melting or it's boiling, there is some amount of heat that's required to make that change happen. However, during that time, it is not changing its temperature, it's only changing its state. So the energy goes into breaking the bonds that hold it in whatever state of matter it is. So the energy required to heat 1 gram or change the state of 1 gram of a substance is called the latent heat of fusion. The latent heat of vaporization is the constant that's used for boiling. We will only ever be looking at the heat of fusion for water and the heat of vaporization for water. So those values are listed here, and they are also on your reference table. So the equation is that Q, again of don't worry that it's a little q versus a capital Q, is equal to mass times the heat of fusion. So the more of matter you have, so the bigger the mass, the more energy it's going to take. So mass times this constant value gives you the heat that it takes and the energy that it takes to undergo the phase change. This is a heating curve. So you can see that if we have a substance, it's going to, if it's a temperature below its melting point, so this is its melting point, so it's a solid down here and it's very cold, it takes some energy if we sit it on, a hot plate or something in order for it to change its temperature and get to the melting point. Then we see here the latent heat of fusion. There is some energy that gets input in order to actually melt the substance. And notice that this line is flat here because the temperature does not change when something is changing its state of matter or undergoing a phase change. Then this would be when it is a liquid, so the energy is supplied in order to bring it up to its boiling point. And then again, a flat curve because the latent heat of vaporization, this is the energy that's going in to change the state but not change the temperature, so to take it from a liquid to a gas. And then this is energy increasing the temperature of the gas. Now, this is called a heating curve because we go from cold to hot. But if we were to look at this in reverse and look from right to left, then we could call it a cooling curve. But essentially, it's the same idea. All right, so let's look at an example of how much energy it takes to change the state of a substance. So it says how much heat is required to boil 25 grams of water. Well, that is just Q equals M times the heat of vaporization. That's a known value. I gave it to you on the slide previously. It's on your reference table. We multiply it by 25, and you get this 56,500 joules. Okay, so that's how much energy it takes just to change the state. And remember, it's not changing its temperature. Now, a little bit more difficult example would be like this. So how much heat energy does it take to raise the temperature of 8 grams of ice from -5, sorry, the negative got cut over here, to 20 degrees Celsius? So what we need to do is we need to think about what's actually happening here. So what is going to happen to the ice as we heat it from -5 to 20? So first, the solid ice is going to heat up. And so we have the heat energy that is required to take that mass of the ice and raise it by 5 degrees Celsius, because we know that's at 0 is when it's going to start to melt. And that C is the specific heat for solid water or ice. So it's a little bit different than liquid water. Then when it gets to 0 degrees, the ice is going to melt. So some amount of energy is going to go into that melting. So the heat of fusion times the mass. And then we're going to heat the water up from 0 to 20 degrees. And again, we would have to use this MC change in T. So if we were to plug it all in, we've got the MC change in T while it's in the ice, plus the melting, plus the heating from 0 to 20. So the first thing I would do is plug in 8 grams of ice is what I start with. This is the specific heat for ice, times 5, because we're going to go from -5 to 0. Then the energy required to melt it. Then the energy required to change liquid water from 0 to 20 degrees. And again, notice that the specific heat here is a little bit different. And then if I were to add all those values, this would be the total energy in joules.